Swayam Prabha. Digital India. Educated India.
I welcome you all to the lecture number 17 in the course Thermodynamics and Thermal Engineering. This is the last topic in the module number 3. What are the contents which we are going to discuss in the lecture number 17? That is the last topic in the module number 3. So, after this we will be studying about the psychrometry, refrigeration, air conditioning, and the last module would be on heat transfer, conduction, convection, radiation, and a few numericals on heat exchanger design. So, before seeing the contents of this lecture number 17, let us have a quick recap of what we have discussed in the previous lecture number 16. So, we have derived the steady flow energy equation for a nozzle. The primary function of the nozzle is to enhance the velocity of the fluid at the expense of pressure. So, we defined the efficiency of the nozzle, which is the ratio of actual enthalpy drop to isentropic enthalpy drop, that is H1 minus H2 dash divided by H1 minus H2. In the nozzle, if we consider the inlet velocity to be negligible compared to the very high value of exit velocity, so then the exit velocity can be written as V2 equal to square root of 2 into delta H, which is the drop in enthalpy from inlet to outlet, So, we have solved one numerical question in which the steam enters the nozzle in superheated condition. We have taken the values of H1 and S1 from the superheated steam table, that is table number 4 and 5. Then we found the dryness fraction at the exit of the nozzle, which was around 85%, that means 85% vapor and remaining 15% liquid. And we have found out the mass flow rate through the nozzle using the continuity equation rho AV. Reciprocal of rho is specific volume, so the specific volume have to be found out. So, let me see the contents of this lecture number 17. So, this is the nozzle, whatever we have discussed, it is a part of this jet propulsion device. So, introduction about jet propulsion, forces, what are the forces acting on an aircraft or an aeroplane, how to produce thrust, what are the thrust producing devices, how the thrust differs from the specific impulse, efficiencies, the propulsive efficiency and thermal efficiency, and few numerical questions. If you remember in the previous lecture, I was explaining about the Mollier diagram. So, there are two ways by which we can solve the problem. One is by using steam table, take the property values from the steam table. Another one is from the Mollier diagram or Mollier chart. So, I would be would be spending some time in this lecture to complete the previous one quickly, and then we will see the contents, because most of the contents in this one are theoretical one, and of course few numericals are very simple one where we do not have to take the property values from a table or from a chart. So, this is before seeing the introduction and the types of thrust producing devices, specific impulse thrust. Let me go to the previous numerical question where I stopped. So, here if you see one table which we have not used is, so here I told to find out the specific volume at 2. So, this specific volume have to be found out from the pressure, critical pressure. Okay, so, this I have taken the critical pressure which we have calculated is, this is the critical pressure, P2 star is equal to 54.6 bar. If you see the steam table, we have, this is table number 2, okay, this is table number 2. So, I have taken the value, actually approximate value only I have taken. The pressure is lying between 54 and 56, 54.6. Either we can take it for 54 or which is an approximate one. The perfect value may be an average of 54 and 56, which will give 55. So, 54.6 if we round off from that one decimal, so we will get around 55. Of course, I have taken for 54. So, there will not be much difference in the answer. So, corresponding to 54, this one. So, this is table number 2, saturated water and steam, because I need to know the specific volume of the this one gas. So, this is the value I have taken 0.036330. So, this is what I have taken here 0.036 meter cube per kg. So, this I will substitute here, that is 1 by specific volume in the numerator, area into velocity. Capital V is the velocity, small v is the specific volume. So, that is how you arrived at the mass flow rate. So, this part was not explained due to shortage of time. Okay. Now, let us focus on the Mollier diagram. There are 4 constant property lines. One is the pressure lines, one is dryness fraction. We have got the temperature lines. We can see the temperatures here. These are all the temperatures. Let me round this. These are all the temperatures. These are all the temperature lines. And of course, specific volume lines are there. Okay. So, because it is not very clear, so I have just explained where the other 3 lines are there. But any Mollier diagram will have these 4 lines. X axis is entropy, y axis is enthalpy. Then we have constant pressure lines, constant temperature lines, dryness fraction lines and specific volume lines in meter cube per kg. Let us see how to take the enthalpy at state point 1 and 2 directly from the chart, I will explain the regions which are there in the Mollier diagram. Primarily there are 2 regions are there. So, you can see one saturation line. So, this is one saturation line, this is the saturation line, this is the saturation line which separates the 2-phase region from the superheated region. The region above this saturation line is the superheated region. This is the superheated region, and the region which is lying below the saturation line is in 2-phase region, where the liquid in the mixture liquid percentage could be more. If for example, if the dryness fraction is 0.25, that means it is only 25% vapor, 75% liquid. If the dryness fraction is 0.95, 95% vapor and the remaining 5% liquid. So, the upper region in this curve is, we have to refer this region to take the superheated properties like enthalpy and all, and the region which is lying below the saturation line is the 2-phase region, So, now the given pressure is, suppose if you take the same problem, the pressure and temperature are 100 bar and 500 degrees centigrade. The values of pressure in the Mollier diagram, are in megapascal. Pressures are in megapascal, and the temperatures are in degree centigrade. Temperatures are in degree centigrade. So, this is in megapascal. Suppose if you take 100 bar is 10 megapascal. So, when we multiply the megapascal by 10, we will get bar, divide the bar by 10, we will get megapascal. So, 100 megapascal is 10 bar, 10 megapascal, 100 bar is 10 megapascal. So, this is the 10 megapascal line, this is the 10 megapascal line, Let me erase this one, otherwise it will be confusing. This is the 100 bar or 10 megapascal line. Okay, so, this is 10 megapascal or 100 bar. Okay, so, this is the line. So, this is the line I am referring. Now, the temperature 500 is here, So, we have to see where it intersects, temperature 500 is here. Okay, so, temperature 500 degree centigrade is here. This is the temperature 500. Somewhere else it touches here 6.6. Somewhere else it touches this region. So, this is the intersection, somewhere else this is the intersection point. Okay. So, this is the condition of steam. See, I have plotted this point corresponding to 100 bar and 500 degree centigrade, 100 bar and 500 degree centigrade. So, the 500 degree line is coming like this. This is the constant pressure line. So, the intersection point is somewhere else here. So, it will be okay. So, when we read the value directly, you can read that this is state point 1, this is state point. Okay, so, this is state point 1, state point 1. So, if you read the value here, it is lying between 3300 and 3400. Okay, from the steam table we have got this value 3375. Okay, so it is lying close to 3400. Okay, and what is the entropy value? If we compare, it is 6.599. There it is coming 6.6, because as I said, in the table we can take it accurately, and in the chart it is an approximate value. Okay. There may be slight difference in the value which we are taking from the Mollier diagram and the table, but marginal difference is accepted, marginal difference is accepted. So, this is the enthalpy value. So, at this value, okay, let me write this one. So, this is point number 1, and this is expanded up to a pressure of 0.5 bar. 0.5 bar is 0.05 megapascal. When you divide 0.5 by 10, we will get 0.05 megapascal. 0.05 megapascal is this pressure. This is the pressure. 0.5 bar or 0.05 megapascal. So, I will refer this curve. So, where it is lying, this curve. So, I am going to fix point number 2. So, here it is coming like this. Okay, so, this is the curve, and you have to see this is the intersection point. How I find point number 2? We know the isentropic process is a perpendicular line. It is a perpendicular line. It is a perpendicular line. So, let me explain here. There is no space. Okay, let me explain it here. This is the process. So, first I have found the P high pressure line, and the intersection point of 100 bar or 10 megapascal and 500 degree centigrade is point number 1. Draw a 90 degree line or a perpendicular line to any distance, then this point will meet the low pressure line. This will meet the low pressure line, that is okay. So, I think it may be, this is 100 bar and this is 500 degree centigrade intersection, and this is 0.5 bar line. So, draw a line from point number 1, perpendicular line, where it intersects the 0.5 pressure 0.5 bar pressure line. So, that is this one. So, that will be state number 2. This is process 1. This is process 1. So, let me. So, this is 1 to 2 for which can be represented on the Mollier diagram, and you can see the value, read the value 1 and 2. The entropy is, this is the entropy line. So, I am getting the entropy as S1 is equal to S2 is equal to 6.6 kilojoule per kg Kelvin. H1 is 3375. So, this value is H1 is 3375 kilojoule per kg, and point 2 the value is approximately 2300. So, if you see, compare the value which we have calculated using the steam table, it is 2291. Here I am getting 2300. So, approximately H2 is equal to 2300. Let me again repeat. If you directly take the x-axis value, that is entropy. If you take the value on the y-axis, that is on the left side, okay, y-axis, that will give you the enthalpy at state point 1 and enthalpy at state point 2. Enthalpy at. So, let me draw this line, and this is the. So, this is how we have to find out H1 and H2. Similarly, we can find the dryness fraction line. Say at point 2, this is the dryness fraction line. This is the dryness fraction. Okay. So, this is 0.85. So, to read out the dryness fraction, I am using this curve. I am using this curve because these inclined lines are dryness fraction. So, the dryness fraction is this value. From the Mollier chart, it is 0.85, the 0.85. Let me erase this one, so that whatever the value which we have found for this problem, I have circulated. So let me erase this one, and here this is the dryness fraction. Okay, this is the dryness fraction. Let me save it, so that when you refer this one, it will be very easy, and it is a very simple procedure to find out the values. And this is the dryness fraction. So here it is 0. This value is 0.85. Our calculated value from the steam table is 0.846. So it is close to the, if you round off this one, it will be 0.85. That is what I am getting from the Mollier chart. Now let us quickly solve the second problem before going into the jet propulsion. Dry saturated steam expands in a convergent. It is clearly given dry saturated steam. So the condition of the steam at the inlet of the nozzle is saturated. Dry saturated means x is equal to 1. In a convergent divergent nozzle from 10 bar to 1 bar, assuming that the initial velocity is negligible and the expansion is isentropic, the critical pressure, find the critical pressure and the throat area. Okay, so this is dry saturated condition. This is saturated condition. It is not, so no need to check whether the steam is superheated or not. Since it is clearly given the dry saturated condition, so the dryness fraction of the steam is 1, so it is in vapor state, saturated vapor. It is saturated vapor at the inlet of the nozzle. So inlet pressure is 10 bar, or the critical pressure ratio we can find using this formula. That is the first question. Find out the critical pressure. Okay. So let me write this one. P1 is equal to 10 bar and P2 will be equal to, what is the pressure given? 1 bar. Critical pressure ratio we have to find out. P2 by P1 whole power star, that is equal to gamma by gamma plus 1, 2 by gamma plus 1. Let me see the value. 2 by gamma plus 1 by gamma minus 1. 2 by gamma plus 1 divided by gamma minus 1. Okay. So for a steam which is in saturated condition, as I said before, gamma value is 1.135. For dry and saturated condition, gamma value is 1.135. We have to take gamma as 1.3 only if the steam is superheated condition, is in superheated condition. Substitute the value, you will get P star. Okay. We can write P2 by P star also. So this is nothing but you can write P2 by P star also. See, P2 star is nothing but P star. At the throat, P1 star, P2 star, P star are all same. Okay. So that is why in the previous problem I have used P2 star, here I am using P star. Okay. So P2 star is equal to P1 into 2 by gamma plus 1 by gamma minus 1, where gamma is equal to 1.135 for dry saturated steam. It is equal to 1.3 for superheated steam. So the values are different for this one. So this is the, so here this one, so here it is dry saturated steam. So substitute the value, P2 star is nothing but P star. So we are getting around 5.8 bar. So 5.8 bar. So that is the critical pressure. It will be less than 10 bar, more than 1 bar. So if you see this line, so this will be less than 10 bar, less than P1. Okay, let me write like this. It will be less than, P star will be, let me write here itself. P star will be P2 star or P star will be less than P1 but greater than P2, So this you have to remember. So, this is 5.8 bar. So, this is the first part of the question. Second part of the question is area at the throat. See, normally the throat conditions, pressure at the throat, area at the throat are all represented by the, because there only we get the maximum, the critical values. So, it is mentioned as, represented as A star or P star, like that, A star or P star. Okay. So, now let us, like from the steam table, since we know the condition of the steam is dry saturated, I will directly refer table number 2, table number 2, table 2 corresponding to the inlet pressure is 10 bar, inlet pressure is 10 bar, read out Hg value and Sg value, okay, yes, Hg value and Sg value. Do not refer the superheated property tables for this case, because it is clearly given at the inlet the condition of the steam is saturated. So, 2776.2, 6.538. So, that is what I have written here. Okay. So, this is from table number 2, this is also from table number 2, this is also from table 2. We know entropy at 1 is equal to entropy at the this one. Instead of writing S1 equal to S2, I am calculating the property at this point, at this point. Okay. So, at this point the condition state point is asterisk, like critical condition, critical. The pressure ratio is P star, the throat area is A star here. So, I am taking from here to here. So, same S1 equal to S star, S1 can be written as SF star plus X into SF G star, okay. And this value also you can take 1.918, okay. And this is the value 1.918 corresponding to 5.8 bar. Here I am not taking the properties at exit pressure, I am taking the properties at the critical, that is the critical, at the critical pressure of 5.8 bar. So, again I am using the same table, table 2, okay, this is table 2, where I have taken the SF value 1.918, 1.918, so you can see here 1.918, okay. SF star, SF G star, or both these values should be taken at P star is equal to 5.8 bar, table number 2. I am taking the property at the critical point, not at the exit point. So, the critical point at the critical pressure ratio is 5.8 bar, 5.8 bar. Now, the dryness fraction at the critical condition is 0.962, that is 96% vapor, remaining 3.8% liquid. So, these properties also to be taken 1.918. This I have taken S1 I have taken from the saturated condition. Okay. So, why I have taken Sg value directly, already I have explained here. See, when we say dry saturated, X is equal to 1. So, suppose I am writing S1 is equal to SF1 plus X at the inlet, the condition of the steam is dry saturated. So, SF1 plus X1 into SFG1. So, this is how we write it for state point 1. Now, here X1 equal to 1. So, this is equal to SF1, X1 is 1, 1 into SFG1 can be written as SG1 minus SF1. SF1 and SF1 will get cancelled. So, the entropy at 1 is equal to the vapor entropy. If if the dryness fraction is 1, then S is equal to Sg, H is equal to Hg. If it is pure liquid, saturated liquid, that means X is equal to 0. That means entropy will be equal to liquid entropy, enthalpy will be equal to liquid enthalpy. So, this you should remember, when X is equal to 0, entropy is equal to SF and enthalpy is equal to HF. Similarly, specific volume will be equal to Vf. When X is equal to 1, specific volume will be equal to Vg, entropy will be equal to Sg and enthalpy will be equal to Hg. So, these should be kept in mind. This is very, very important. That is why if you see this one. So, now I have taken, we need the specific volume properties corresponding to 5.8 bar. So, that also we have to take. Okay. So, that also we have to take it, where I have mentioned here specific volume from table number 2, 0.32752, 0.32752, where is the 5.8 pressure line. So, this is the specific volume. Corresponding to 5.8, that is a critical pressure. So, that is what I have taken here, and the velocity of the steam at the exit is V into square root of 2 into H1 minus H2, the same formula, exit velocity. Use the equation of continuity whenever we want to find out the area of the nozzle, if whether at the throat or at the exit, continuity equation to be used, rho into A into V, that is density into area into velocity. Density is 1 by specific volume value can be taken from the steam table or also from the Mollier diagram also. If you are using steam table, you have to take all the properties from steam table. If you are using Mollier diagram, we can take the properties from the Mollier diagram, but do not take one value from Mollier diagram or steam table. Of course, sometimes you will get the perfectly same value, sometimes there will be variation, there will be little variation in terms of decimal places. So, now one specific volume we are finding at the critical pressure, that is small v star. So, this is rho v, small v star is equal to 1 by rho star, okay, 1 by s star. So, I know the mass flow rate is given in the question, mass flow rate is given as 5 kg per second, mass flow rate is given as 5 kg per second. So, m dot is equal to 5 kg per second, which is given. So, this is m dot, okay. So, this is m dot. So, I get the area at the throat is 0.0038 meter square. So, the same problem can be solved by using Mollier diagram, okay. I will just Mollier diagram or Mollier chart, both are same, okay. So, these are pressure lines. Here the inlet pressure is given as 10 bar. So, if you divide by 10 in terms of megapascal, it is 1 megapascal. So, identify the 1 megapascal line. This is 1 megapascal, this is P1 equal to 10 bar or 1 megapascal, and the temperature line we can find it, and this is the saturation line, So, the dryness fraction of the steam at the inlet of the nozzle is x is equal to 1. So, easily we can find this line, intersection of this point and here. So, you will get H1s between 2700 and 2800, that is what we are getting here. Okay, what is the enthalpy? Here the enthalpy is 2776. So, if you plot this one, this is the line, 1 megapascal line. So, where it is intersecting the saturation curve x is equal to 1, it is intersecting at this point, it is intersecting somewhere else, this point. So, this is state point 1, okay, this is state point 1, and the extent up to 1 bar is 0.01 megapascal, sorry 1 bar 1 by 10 0.1 megapascal, in the previous case it is 0.5. So, divide by 10 you will get 0.05. Here the exit pressure is 1 bar, okay, exit pressure is 1 bar. So, which is equal to 0.1 megapascal, 0.1 megapascal. 0.1 megapascal is coming, this is the 0.1 megapascal line, 0.1 megapascal or 1 bar. So, this is P2. So, we have to draw the process from 1, we should know where the point 2 comes. So, for that we need to take the exit pressure, and since it is an isentropic process, it is a line should be perpendicular to x axis. So, draw a line where it intersects the exit pressure 1 bar or 0.1 megapascal. So, if you take this one, in this case this is the line,
this is the line. So, it will come up to this point. So, this is point number 2. So, this is the process, and here the enthalpy is close to 2800, and if you see the value which we have taken 2776, okay, it is close to 2300. So, I am getting approximately 2000, okay, 2800. So, H1 is approximately equal to 2800 kilojoule per kg, and the entropy value I am getting around, so the entropy is 6.59. So, I am getting around 6.6. So, here it is around 6.6. Entropy S1 equal to S2 is equal to 6.6. This value 6.6 kilojoule per kg Kelvin. So, that is how we have to find out. Similarly, we can find out the critical pressure ratio. We have calculated it is at 5.8 bar. So, similarly you can find out 5.8 bar line or 0.58 megapascal line, and that will be somewhere else between 1 and 2. So, that is how we can solve this problem. Okay. So, here the propulsion is the refers to the movement of an object in the forward direction. I mean, it is the moving the forward like a pushing or this one object which is in motion in the forward direction, that is the referred to as propulsion. Jet propulsion is the movement of an object in the forward direction by a jet of fluid which is induced or exhausted in the opposite direction. This is like Newton's third law of motion. For every action there is equal and opposite reaction. So, when the if the vehicle has to move forward, there should be an opposite reaction. So, because of which the thrust is produced, the thrust is produced in the forward direction, whereas the jet of gases, we call it as jet of stream, fluid jet, which is exhausted in the reverse, in the backward direction, This picture shows the 4 forces which are acting on an aircraft vehicle. Acceleration due to gravity in the downward direction, opposing the acceleration due to gravity, that is the weight of the vehicle. Weight is mass into acceleration due to gravity, m into g, and in the vertical for upward direction, lift is acting. Left side in the forward direction, thrust. So, opposite to the thrust, drag is there. So, these are the 4 forces which are acting on an aircraft, and we know the weight is W equal to m into g. So, this is due to the acceleration due to gravity, the object which is attracted due to g, and lift. Without lift, the aircraft cannot take off and fly, and drag is the force which is in the form of a resistance offered by the air due to friction. So, it try to oppose the forward motion of the vehicle, which is the thrust. So, thrust is the force which is developed or produced by the engine. And let us see the thrust producing devices. There are a lot of thrust producing devices like a propeller. We have got a jet engine, turbojet engine as shown in this schematic, turboprop engine, turbofan, turbo shaft, then ramjet, all these things are used. So, in the lecture number 17 in the content, I have taken 2 types of thrust producing devices. One is turbojet and another one is turboprop. And we will be seeing about what is a specific impulse, what is the how to define the thrust force or whatever it is, propulsive efficiency, thermal efficiency, and simple numerical questions before we wind up. So, this is the thrust producing device. Primarily it consists of an intake, a compressor is there, turbine, combustion chamber. Before the turbine we have the combustion chamber. Just a quick recap of the gas turbine cycle. We know in a gas turbine cycle, if it is a closed cycle, we have 4 major components, 2 heat exchangers, 1 compressor and one turbine. If it is an open cycle, the bottom portion heat exchanger is not there. Of course, in the actual case, the combustion combustion process is there, which is replaced by a heat addition process. In case of a Brayton cycle, we have derived the efficiency, thermal efficiency also 1 minus 1 by pressure ratio power gamma minus 1 by gamma, and the exhaust process is replaced by a heat rejection process. Both are constant pressure. So here the air is first taken, admitted inside this one, where it is compressed to high pressure, high temperature. The high pressure, high temperature air is taken to the combustion chamber, where the fuel is sprayed and the combustion takes place. The exhaust gases, or then from the combustion you can see the blue color arrow mark, the exhaust gases which are taken to the turbine. This is the turbine which produces the work in the turbojet engine. The turbine is a power producing device. The power required to drive the compressor is used from this turbine only, and as the gases are exhausted from the system, there will be a nozzle which is not shown, where the fluid velocity will be increased. So the nozzle portion is not shown in this one, but of course a nozzle will be there to enhance the velocity at the expense of the pressure, and then it will be exhausted. So it is like this one, like a open cycle. So the admitted air is compressed to high pressure, high temperature. Then the air along with the fuel which is sprayed in the combustion chamber, it goes for combustion. The gases are expanded and then it is exhausted. So this is how. So this certain mass of gas, it is leaving this one in the opposite direction. This is the primary reason for producing the thrust produced by the engine, which pushes the vehicle forward in the forward direction. And the second one is the turboprop engine. The difference between a turboprop and turbojet is the power produced in case of a turbojet is used to drive the compressor only, and we don't have this like a propeller which is shown in this one. So here the power produced by the turbine is used to drive the compressor as well as the propeller. So that is the difference between. Of course, there are other differences, like if you take the turbojet engine, normally it is used for higher altitude and high speed applications, or like a long haul application, where like mostly not for a commercial one. Of course, it can be used also. Mostly for the commercial, this one like for a medium speed or a little slow speed, not for high speed or not a very high altitude, where turboprop engine are very efficient. Whereas in case of turbojet engine, so normally those are employed for long haul journeys, and those type of engines without any interference, it covers a longer range. When I say longer range, it can be used for a very long journey without intermittent refueling stoppage. So in terms of the construction, this one, there is one propeller which is provided, and of course there is a gearbox also. There is also a gearbox to vary the speed. So the power from the turbine is used to drive both the compressor as well as the propeller. So here, this is the diagram which I have taken from the Wikipedia. So I have given the reference. Thrust, how to calculate the thrust produced by the engine? It is the rate of, like we know, F equal to ma. A is the rate of change of velocity. Product of velocity into mass is called momentum. Momentum is nothing but product of mass and velocity. So rate of change of momentum of the jet coming out of the nozzle. There are two velocities which are involved. One is Vj and another one is the Vj is the velocity of the jet coming out of the nozzle. I told little before that certain mass of the gases which are coming out of the exhaust, it has a mass into it is coming out with a velocity. So that is the momentum which is in the opposite direction, and which is the primary reason for producing the thrust which makes the vehicle to move in the forward direction. So V suffix j is the velocity of the gas jet meter per second. V aircraft is the velocity of the aircraft. So the difference between this one multiplied by the mass is the rate of change of momentum of the stream which is coming out of the nozzle or the exhaust. What is the difference between the primary difference between the aircraft and rocket is? So, here you see also, here also you find the combustion chamber, exhaust, all these things and all. The difference is the rocket engines carry both the fuel and the oxidizer. It carries on the flight when it is on travel itself. So, it does not take it from the outside. So, the oxidizer is also carried by the rocket engine. So, here we have got I have shown the red color portion, that is the combustion, the gases after the combustion, where the fuel is sprayed like this one, where it is mixed with the air and the combustion takes place. The combustion gases are then expanded. So, here I have shown the nozzle portion. So, here you can see the diverging portion of the nozzle, which is in green color. So, like the function of the nozzle is to increase the velocity of the fluid when it comes out of the nozzle due to the pressure drop, same concept, and it is leaving at exit pressure PE, velocity is VE, and the area at the exit is AE, and of course P naught here refers to the free stream condition, that is the ambient condition, this is the exhaust portion. So, the thrust in case of a rocket is primarily produced by two things. One is, this is due to the momentum, this is due to momentum, mass into mass of the gas which is leaving the nozzle, which is leaving the exhaust, multiplied by the exit velocity, the velocity at which the gases comes out leaving the nozzle. This is this one, and this is the pressure thrust. This is the due to the pressure thrust. So, difference between the pressure that is P and P naught multiplied by the exit area. So, primarily the thrust which is produced in this region due to the pressure thrust, the total thrust is the summation of momentum, thrust due to momentum and thrust due to pressure. So, the second one, it depends upon the delta P, okay. Pressure is force by area, force equal to pressure into area. So, that is the formula which I have used. So, with this one let me derive a small derivation, specific impulse. So, the thrust here, it is the momentum due to the momentum, and this is due to the momentum, change in momentum and the pressure thrust. Okay, this m dot v naught is equal to 0 generally. So, it is not for rocket engine, there is no free stream air brought into the propulsion. It carries its own fuel and oxidizer also it is carrying. So, therefore, m into v dot is equal to 0. Okay, so this is of course m dot. So, when I say this one, it is m dot. Okay, mass flow rate, you can take m dot as itself. So, this equation reduces to this term will become 0, m into v dot equal to 0. So, m into v plus primarily the equation which I have written here, I have got this one. There are actually three terms: mass flow rate into exit velocity minus mass flow rate into the free stream velocity plus delta P, the thrust produced due to the pressure difference. So, now I have got this equation which I explained before, which was there in the previous slide. Divide this equation by m dot, okay, sorry, divide this equation by m dot, okay. Due to some compatibility, this dot is not there, so I am just mentioning with the pen. So, divide equation 2 by m dot. So, m dot will get cancelled, P minus P naught by this one, it is a very simple derivation. So, on the left side you will get thrust, that is F divided by m dot, okay. So, it is mass flow rate, not mass, it is mass flow rate. M is mass, m dot is mass flow rate, m is in kg, mass flow rate is in kg per second. So, now I have got F by m dot is equal to VE plus P delta pressure difference into this one, the whole term. Okay, let me put a bracket here. So, this there will be one square bracket here. So, this entire term is divided by m. So, here I will put a bracket. Okay. So, here I will put a bracket P minus P naught by into A divided by m. Of course, it is understandable. The first term m term get cancelled. because okay, m dot into V by m dot will get m dot. So, the right hand side I am writing as equivalent velocity, where what is equivalent velocity? Where equivalent velocity is equal to V e plus this term P e minus P naught into A e by m dot, P A by m dot. Of course, this bracket is not required, but sometimes it may be confusing whether this summation term is only for the numerator, it is this entire term. So, this is the equivalent velocity. So, now from this find out f is equal to m dot into equivalent velocity. I have brought the mass flow rate term to the right hand side. Okay. Now, I am defining the impulse. Impulse is nothing but force into time, force acting for a time period, force acting for a time period. So, impulse is f into dt, impulse. Now, I substitute equation 3. From equation 3 I have f equal to m into equivalent velocity. So, instead of f I will substitute m into equivalent velocity into dt. So, that is in 3 is substituted in equation number 4, I am getting this one. Here again this is m dot, okay, this is m dot, this is also m dot, okay, m dot by t. This is assuming that, see I am substituting, let me repeat it again, I am substituting equation 3 in 4. So, I equal to, instead of f I have got m dot into V equivalent into dt, into V equivalent into dt. So, this is assuming the equivalent velocity remains constant with the time, and integrate equation 5, integrate equation 5, integrate equation 5. So, here I will get 1 by t into dt, integration of dt is t, t and 1 by t will get cancelled. So, I will get m equivalent into impulse is equal to m equivalent into V equivalent velocity, equivalent velocity. Okay. So, here it will be, let me repeat it again, from equation 3 I am getting the thrust in terms of mass flow rate and equivalent velocity. I am defining the terms impulse, that is nothing but a force acting on a particular time. So, force into dt integral. So, instead of f I am substituting this m equivalent. What is m dot is equal to m by time. Okay, let me write m dot is equal to m by time. So, instead of m dot, okay, so here it is m dot, here it is m dot. I am replacing this mass flow rate as mass by time. So, m by t, and when we integrate dt we will get t, integral of dt is t, already I have got 1 by t. So, t and t will get cancelled. So, I will get impulse in terms of mass, not mass flow rate. Okay. So, the error is regretted. So, this t and the integral of dt will get cancelled. So, m into V equivalent, m into V equivalent. Now, this is equation number 6, divide this equation number 6 by mg. So, left hand side I have got I by mg is equal to m into V equivalent divided by mg. This mass term will get cancelled. So, we are having impulse divided by mg is nothing but specific impulse, that is specific impulse per unit weight, impulse per unit weight is nothing but W equal to m into g, mass into acceleration due to gravity, that is nothing but right side the m term will get cancelled. I am getting equivalent velocity divided by acceleration due to gravity. Now, I am substituting again 3 in 7. What is equation 3? Thrust is equal to mass flow rate into equivalent velocity. Thrust is equal to mass flow rate into equivalent. Substitute 3 in 7. I get the specific this one as f by m into g, f by m into g, where I suffix sp is the specific impulse, which is the ratio of specific impulse is the ratio of thrust to the weight of the propellant, weight of the propellant. Now, let us see the difference between the propulsive efficiency and the thermal efficiency. Propulsive efficiency is the ratio of propulsive power to the work done on the fluid. Propulsive power is mass into velocity, that is velocity of the jet, the difference in the velocity of the jet and the velocity of the aircraft, divided by the mv square by 2, that is change in kinetic energy, change in kinetic energy. So, kinetic energy is the jet velocity v square, jet velocity vj square minus the initial velocity, this is aircraft. Okay, so let me write it this one, otherwise it will be confusing. This is aircraft AIR CRAFT. Okay, because if we use the symbol A, normally it refers to ambient air. So that is why I use the subscript aircraft. Okay, V aircraft is the velocity of the aircraft, So this is the change in the kinetic energy, that is the work done on the fluid. So simplify, you will get the propulsive efficiency as twice the velocity of the aircraft divided by summation of jet velocity and velocity of the aircraft. Thermal efficiency, it is the rate at which the kinetic energy is produced, that is, we know efficiency is the output by input. How much the rate at which the energy is produced for the heat supplied by the fuel. Heat supplied by the fuel is the mass flow rate of the fuel into calorific value. Mass flow rate of the fuel is in kg per second. Calorific value is kilojoule per kg. Okay. Rate at which the kinetic energy is produced is half mv square. Half m into v square is jet velocity square minus aircraft velocity square. So that is what this is the formula. So a turbojet engine moves at a speed of 290 meter per second. The exit gas velocity is 490 meter per second. If it consumes air at the rate of 31 kg per second, find the thrust, propulsive efficiency and thrust power produced. So it is a very simple problem. Okay. Mass flow rate of the air is given, consumes air at the rate of 31 kg per second. Mass flow rate of the air is given. Jet velocity is 490. In vehicle velocity is, I have taken as the velocity of the aircraft, that is 290 meter per second. Mass flow of the gas, the mass flow of the gas is a mixture of mass flow of the air and the fuel. Okay, because for combustion we need both air and fuel. If mass flow rate of the fuel is not given, then total mass of the gas is equal to total mass of the this one. Of course, this is mass flow rate. Okay, so I will be using dot here. This is dot. Propulsive thrust total mass of the gas into the velocity difference, that is jet velocity and aircraft velocity, both are given. Mass of the gas is nothing but mass of the air if mass of the fuel is not given. Okay, since mass flow of the fuel is not given. So this is simple calculation. So MA will become mg, which is 31 kg per second. Difference in velocity you will get in kilonewton. Propulsive efficiency, substitute in the formula, all the terms are given. And thrust power is the thrust into velocity of the aircraft. So this is also given. Thrust we have calculated as 6.2 kilonewton. So you substitute this one, you will get it in kilowatts. Next one is the aircraft flying at a speed of 520 km per hour at an altitude of 8,000. The diameter of the aircraft propeller is given. Flight to jet speed ratio, that is velocity of aircraft divided by velocity of aircraft divided by velocity. This is flight to jet ratio, it is given. Density of air is given. We have to find out the mass flow rate of the air, that is m dot, thrust produce, specific thrust, specific impulse and thrust power, specific impulse and thrust power. So here also wherever m term is there, that is m dot. I have given the formulas. So these are all self explanatory. This is m dot, g m dot. Okay. So it is primarily, similarly the mass flow rate of the gas is the summation of mass flow rate of air plus mass flow rate of the fuel, So let me correct this one. So m dot, wherever m is there, it is m dot. Okay. There is some error in the compatibility due to the compatibility of the system. So we can calculate the thrust using the same formula, specific thrust and specific impulse. Specific impulse is the ratio of impulse, it is the ratio of the thrust by the weight of the vehicle, that is specific impulse is F divided by m into g, that is W. Thrust power is thrust into velocity of the aircraft, same formula. Okay, so there are 3 more problems which I have given, you can refer it, very simple problems, numerical. Okay, so to summarize this one, we have seen how to solve the numerical question using Moliere diagram. We have seen the thrust producing devices, turbojet engine, turboprop engine, what is the difference between propulsive efficiency and thermal efficiency, and here we have solved some numericals. So, let me again say here all these things, it is m dot f, it is not mf, it is m dot f, and similarly in the next question also it is mass flow rate is m dot, this one is in m dot. So, let me correct it so that I have given total, due to time constraint I could not cover the numerical questions in detail, but these are all very simple problems, you can refer it. With this, let me conclude lecture number 17. Thank you.
Hi, my name is Lec17 and I teach sociology at IIT Kanpur. One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So, if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So, that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So, let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. Can I just pick up my bags and hop on the next plane and go to South Africa? Any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So, we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other, correct? So, when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.